Good afternoon, everybody. And I can actually see you, which is a real luxury as a Zoom presenter. So I'm curious, I'm looking over my other screen here. How many of you are imagers today who have astronomical cameras and capture spectra images? Any of you? There's one. Good. Great. And I'm going to talk today a little bit about something which, whether you have a camera or whether you're just interested in the topic, can be really valuable in terms of your understanding the sky and how we know so much about the stars. So I'm Tom Field. I'm a former contributing editor at Sky and Telescope, and I'll tell you a little bit more about my history as we go forward. But all of us are familiar with these kinds of iconic images. Just such gorgeous, and I'm just getting my desktop set up a little bit more. This enormous power of creating stars that we're privileged really to be able to witness here on Earth. But with a little bit of my tongue in cheek, I always wonder, what about all these stars here that don't get the limelight, that aren't getting any attention? They or any attention. They have their own life stories and they deserve to be heard or want to be heard to anthropomorphize them a little bit. But what about them? Well, you know, this is a quote you've probably seen before. It's well known and it really applies. And we're going to see a little bit about how it applies as we go through things today. Um, if I was in this image, I'd probably be like on the backside of this building wondering where everybody is. But we really have this, I guess the word is, I'm not going to unfold it very much, but ennobling, this amazing history of how we ascended and are still ascending this mountain of knowledge, having started out on the plains over millennia, many millennia, tens of millennia. So for me, I always, I've been an amateur astronomer for a while, not all that sophisticated, but I've always wanted to know more about the stars, and probably many of you are in the same shoes. And there are so many different ways to do that. Going to events like you're at today, and really, I encourage you to not be shy about going up to people, whether they're formal there or whether they're just part of the crowd, and just saying, "Hey, can you explain to me?" You'll find you'll find that, as you probably already know, that nerds love to talk about what they love. So, and there is so much to be learned. I want to show mostly examples today of what the kinds of things we can do. This is the beloved Orion Nebula and the three belt stars there I've circled. And you can see there they are in this image, which when we enlarge it, we can see over on the right these colorful rainbow spectra. That's what we're going to talk about today, how we produce them, what they mean, and just the secrets that they hold is really remarkable. They say that about 80% of what we know of the stars is from studying these rainbows, which always astonishes me. In fact, I'm a little bit nervous saying that because it seems like such a high number, but I've read a little bit and I ask around people who actually know things. And unlike me, I'm just faking it. And honestly, I think we all have this complex, of imposter complex. And I think part of that is because the more we know, the more we understand how little we know. And so that's, I think, where the imposter complex comes from for many of us. I want to show you another example here. This is a star field. Now, whether you know these constellations or these star fields, the idea is just to give people who are familiar with the sky a little bit of a stake in the ground so they know I'm not just showing dots of light in the sky. So on this image, I'm going to play devil's advocate for a second. What do we have here? It's a bunch of boring dots, right? I mean, it really is. Let's be frank. A bunch of maybe constellations or asterisms, mini constellations without names, just patterns in the sky, random patterns. But there's really nothing there to capture our attention other than, what we can read into it with our imagination. So we're going to look at these three stars just for a few minutes to get a little bit more variety and experience in what these things can tell us. And then we'll delve a little bit more into how we do this. And hopefully this will be something where you'll get to build on your understanding. There won't be a quiz at the end, thank goodness for all of us. And the idea is that you just come away with a new appreciation, as well as perhaps a recognition as an imager that this is something you can do for yourselves. So there are the three stars. This is the full image. And this was captured by just a DSLR and our little grating I'll talk about in a moment. It's captured by a gentleman named Christian Boyle. And we're going to look at each of these stars, starting with this one up here. You're going to see how little I've learned over the years as to how to control my mouse during these presentations. That star right there. So if we look over here at its spectrum, its rainbow, we can see in some places some dots or some gaps, right? There's a gap there and there. Those are actually fingerprints that are what help us read the star's history. We'll get into this a little more later, but you can see that each element, not that we have to be chemists to do this or astrophysicists, I'm proof of that, but each star has its own fingerprint because each element has its own fingerprint. So I want to talk about maps for a second. Years ago, my wife was leaving a shopping mall where she had gone, a new one, and she used her GPS to get there. It was, on the outskirts of town. And when she came to the exit, leaving to get onto the real streets again, she realized she didn't know which way to turn. She didn't have a cognitive map, The GPS was doing the work for her. Maps really can serve us well, especially as you'll see in the next few moments for us when we're studying the stars. So this is the beginning of a map. These are just the stars in temperature order with a funny numbering scheme, which you may be familiar with or not, doesn't matter. It's sort of backwards in that we have low temperature stars at this end and the hot blue stars at this end. But this is one dimension to a map. Now, the second dimension I want to add, this is going to be not going to be a lot of graphing theory, I promise you, is a brightness scale. So for each temperature star, we're going to plot in here different brightnesses that they can be. And there it is. It's a gorgeous, just aesthetically gorgeous map. And it shows us, again, this scale here is how bright they are. And this scale here is temperature. So we can see, notice that, and we're not going to go into a lot of this, but I just want to get the sense across that there's a pattern here, which we've discovered. Most of the stars lie on that main sequence line, but many don't. And understanding why that is to understand the stars. And it doesn't take a lot of science or math or astrophysics or chemistry to gain that understanding of the skies. And with a map like this, the reading that we do going forward, whether it's Wikipedia or, Sky and Telescope Astronomy magazine, we have a way to think about the stars they're talking about. Here are just a couple of our favorites, namesakes that you may be familiar with, either from popular movies or from astronomy. Betelgeuse. It's a cool type M star, but it's very bright. Look how high up it is on this scale. And that's because it's big. It's not bright, but there's a lot of it. And just one or two others here. I'm going to look past my camera, which I have here so that you feel I'm actually talking to you. And I am, even though I'm staring into an empty camera like most newsreaders are on TV. Where's my mouse? There we go. There's Vega, one of the brightest stars in the sky. There's our sun. So you can see there's lots of different places on this graph. We're not going to spend a lot of time with this, but it's nice to appreciate, if you've never seen this before, that there is an order and that we've discerned it. Let's look at the second star for a second. This one down there. This one doesn't have those gaps that we saw up here like that one, right? It's got a gap or two, but it's also got this bright spot, right? Without getting into the details, that tells us that it's a warmer, a hotter type B star, and it has that E at the end of its designation, and that stands for emission line. It's got a glowing circumstellar disk. It's glowing just from the heat of the star. Most stars have these emission or absorption lines called gaps. This one, because it's got this disk far away from the star, is glowing. Where does that fall on our HR diagram? Well, that's a B star, so it's somewhere up above this B. And so it's somewhere in this area. So we've now seen stars in two different quadrants, right? So we're just beginning to get the lay of the land. And the third example to look at, this one down at the bottom, this one is, I should just not circle, not betray just how uncoordinated I am. So this is called a Wolf-Rayet or Wolf-Rayet star. And it has a lot of bright spots, very different than the other two we saw. And you can see these kinds of things just with a very small telescope. You could see it at a star party or at the observatory, the NJAA observatory. Is it NJAA? Anyway, so what's this star?
NJAA.
Thanks. I was going to go NCAA, and I went, no, that's not quite right. So, what about this star? What do we know about it from those emission lines, those spots? We know that it's a late stage star that's, getting ready to die, and it's blown off a lot of its outer shell. It's 25 times the size of the sun. And I'm looking over here at my notes. I am cribbing from my notes. But this is a star that we can see down towards the core. And so we're seeing a lot of things that we might not otherwise see earlier in the star's life. And without getting into all the details, this is the kind of thing that gives us the opportunity to read and understand a little bit about these stars. And I found, much like my wife leaving that mall, that when you have a map, all of a sudden you know where you are and you know how things start relating to each other. So this is a really hot star. So on the this is called the HR diagram. That star is really hot. It's probably in this area and way up here. So we've seen stars in a variety of places, haven't we? And there's other places that we'll look at as we go through today. So that's a really nice, I hope, gentle introduction to just qualitatively how we do what we do. So how do we do that? Well, I'm going to use this little grating. It costs about $195. And it just screws onto your camera. And I want to show you how it works. I hope. Hey, Jimmy, if I turn my screen sharing off, do I go full screen with the audience or not?
I can make that happen.
Yeah, let's do that just for the fun of it. It's a little bit more fun. So there's my screen sharing off.
Yeah, but sit up, man.
Let me move this.
I hope. Sorry to surprise you with this.
Oh, you're good. We'll work it out.
Okay, let me know when they can see me full.
We can see you.
Yeah.
Okay, great. This is a gas tube. And I'm going to turn it on. And then I'm going to bring this star analyzer grating, which acts like a prism in front of it. See all those lines showing up there? Those lines are the spectrum that this prism-like device is splitting the starlight into. That's what we study. And this happens to be a helium gas tube, pure helium. It's like a little fluorescent light, but it's glowing in a single gas. Okay, let's go back to screen sharing if we can, Jimmy.
Roger.
Let me know when we're there.
As soon as I learn how to control the screen share.
I think I'm sharing again, maybe not. Looks like maybe I'm not, so let me get there.
You are, you're good.
Oh, okay, you've got this star analyzer screen. There we go. So just real quickly to show you how things get hooked up, we can put them on DSLRs. We can put these gratings on standard astronomy cameras, DSLRs on telescopes, even video cameras, or a filter wheel. So there's lots of ways in mounting these kinds of pieces of hardware. And it's really easy. It's not rocket science. It's not like we have to get out micrometers and slide rules to date myself, do a lot of calculations. So a little bit of history here. Sir Isaac Newton is said to have discovered that we could split white light into its multiple colors using a prism. We can also do that, interestingly, with any finely lined surface. Here, we're just bouncing the light off a DVD, but you can also pass it through a finely lined surface, and that's what this grating here does, is it just has a lot of very fine lines inside the plastic. Some of you may recall Bunsen's name from the Bunsen burners that he discovered or invented. He burnt a sample and he split the light in a prism and he looked at the result. He was a real pyromaniac. He burnt everything he could find. And this was the beginning of spectra of science, where we were actually categorizing things. And an interesting fact about Bunsen, and that is that after he invented the Bunsen burner, he deliberately did not patent it. He said, I want this for the betterment of humanity. Now, today he would lawyer up, right? He'd appear on Oprah or maybe the Kardashians. They're the ones chasing celebrityship. Bunsen didn't care. He wanted to help humanity. So these are fingerprints that we see when we use a grating or a prism. And all across the top there, you can see we've actually named the features in hydrogen. And we'll talk about where they come from in a moment. And you'll see why these are so important. But you know, this one right here, this beta one, we're going to be talking about that a fair amount. So I want to give it a name. I would say that color is, let's call it robin egg blue, okay? Just to be scientific about it. And that way we'll remember when I come back to it. Here's another example of the deepest science we'll do. And all I want to show you here is that different elements have different fingerprints. And there is that robin egg blue hydrogen beta line on hydrogen. Every element has its own color scheme. And if you happen to be an educator or like to collect things like this is actually a poster that we sell. We actually built it using our software years ago. So what does every single astronomer I've talked about so far have in common? They're old white men. So I think it's important that we look at others just to recognize that we're just looking at a tiny subset. Some of you may be familiar with this. Annie Jump Cannon on the left and her team of computers, that's what they were called. They were prohibited from accessing the telescopes at Harvard. And so they went about studying spectra. And so that's what Ms. Cannon is doing here. And that's what they're doing here. These were posed shots I read recently. But they are studying spectra, and they studied literally 300,000 or 400,000 spectra over the years. And with that deep exposure on photographic plates, glass plates, with that deep exposure and with the creativity and the understanding that they brought, they really came up with some star classification schemes that are important. Priyamvada Nataraja, she's at Yale and studies hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA in the late 1940s. Imagine that, a woman astronomer, how much of a challenge it must have been in that era to hold her own. She must have been a remarkable woman. And Jedediah Eisler at Dartmouth, also studying black holes. And finally, Elisa Quintana studies cooler red M stars and the exoplanets, the planets that might be circling around them. Now, NASA published a poster that imagines what a planet like that might look like. This is the first, and she discovered this, as I recall, Kepler 186f. And again, there's more green light hitting the Earth than any other color, so that's why our planets are green. And you can see here on this red planet, things would be a little different, wouldn't they? It's a fanciful drawing, but it's sort of fun. Okay, enough about all that theoretical stuff. Let's talk about what we can actually do, what you can actually do with some of the equipment that's probably within about 50 yards of you. Here's what I'd like you to come away with really quickly. I'm not as dumb as I look. I'm not going to read all these bullets, but you've already heard me talk about that. It's not hard. It's something you can do. It's really inexpensive and really cool on this. Because we're not looking for that exquisite detail that visual images require, all the subtle gradations, we're able to do it from light polluted skies. So we don't need the kinds of pristine skies that produce images like this. So here is what happens. We put the grating in the light path. And so there's our star, there's the grating, and the light, some of it actually ends up on our sensor just straight through. That's the star itself. And then we get this rainbow that comes out, and ends up looking like that on our sensor. Now, we don't need a color camera. In fact, it's better to have a mono camera. We know that the first light that we'll see here is blue and the light that's over here is red. So when we're studying it, it's really easy to determine the colors, even though we don't see the actual color itself in our images. I'm going to show you a really cool image. It's pretty and it's really significant. This is each a different star spectrum captured at a different time by Torsten Hansen. And he did this with a really small telescope, with relatively small, 8 inches, and a really old video camera. This is something, imagine a video camera. That means that, there's frames going by, a frame every 1 or 2 seconds. We're not talking about having to take these long exposures. So without getting into a lot of detail, this is the kind of thing that in the late 1800s, they looked at and went, look at that. Not only are the stars different temperatures, some red, some blue, etc., but they have different gaps. So now we can study those gaps to know something about the star's composition. 2 quick examples on the screen. One is these forests of lines on these cool stars. Now, in the next 10 seconds, I'm going to tell you everything I know about those lines, and that is they're what's called titanium oxide, relative to what goes into suntan lotion, if that word isn't archaic. That's all I know about them, because I chose not to read more about them. I find it fascinating enough to know just that they can't survive on the hotter stars up above, because the hotter stars burn up that titanium oxide bond. And the other thing to show you is that this, where is it? Oh, what a mess. This line here, this gap, doesn't even appear down in these cooler stars. And in fact, it's the darkest and widest on these A-type stars like Vega, the brightest star in the sky. If you go out tonight in the evening when it's dark out, a little bit to the west from overhead, you'll see the brightest star, and that's Vega, that has this really dark gap. And what color range is that in? That's the robin egg blue, hydrogen beta. So how do these gaps come about? Really quickly, that you may recall the Bohr model of the atom has these shells and orbits that electrons are going around in. And when they jump between shells, they absorb light. And when they jump between shell 2 and 4, this is the color of light they absorb. They need energy to climb up there, or to get pulled away from the nucleus of the star, of the atom. So that's all the deep science we're going to talk about, but we are not going to close our Zoom presentation in PowerPoint when we're trying to advance to another slide. So let's move on to the next slide, and that's here. 2 other quick things. Sometimes you see gaps, and I don't know where my mouse got to. Sometimes we see gaps in our spectra, and sometimes we see dark areas with bright spots behind them. And which we see depends on, let's go back a slide here, which we see depends on whether it's gaps or whether it's lines, depends on things we won't talk about, but temperature, the gases, the lights going through and stuff like that. But the thing about these that's sort of cool is that regardless of whether it's gaps or bright lines, they're at the same spot. And we'll see examples of both those in the next few minutes. So here's our setup. Now, suppose, let's just do a thought experiment here. The Hubble Space Telescope people, suppose they made a huge, huge mistake and they gave me, Tommy Field, time on their Hubble Space Telescope to capture data. Big mistake. And I captured some images and I said to them, hey, look, there's a little bit of dimming right in that robin egg blue area. Would that be publishable? Nope. So we can't just say, it's about that color and I see a little dimming. It's not really a dark dimming, but it's sort of a little. We need to do science. And to do that, we create a simple graph. I can hear whoever that is. So this is a big peak. This is basically how bright is this air, this color. Big peak here because the star is bright. Bill can hear you in the background. And this deep dip here is right where those crosshairs are. Now we can do science. We can study where that dip is, how wide it is, how deep it is, how it looks tomorrow night, how it looks on a different telescope and on a different continent. Is it a supernova? What would that gap look like? Would there be a gap? So every star has a different spectrum. This is a well-known constellation, and you can see each of the Pleiades stars has its own unique spectrum. So how do we capture those spectra? Now, look, I know it's after lunch there, and if I get into a long software demo, if Jimmy had a mic in the front of the room there, I'd start hearing snoring and people's heads hitting the chairs in front of them. So I'm not going to do a long software demo, but I do want to show you. Yes.
I have a cane, so I can just hit him.
Oh, perfect. Great. It's not going to be a long software demo, but I think it's important that you see how easy it is. And that is, here's an image that came from our telescope. Could be mono, could be color, could be video. I use color here because it's more intuitive. You go, oh yeah, there's that blue to red rainbow Tom's been talking about. And you can even see a gap right there and maybe some here. So all we do, now we can do this live under the stars. We just bracket it with these little capture lines. And now we see that graph. Well, remember, this peak here is the star. And this dip here, let's go to this dip right there. That dip is because there's a gap right there. Now we're doing science. But the final question is, WTF, so what? They're gaps. What do they mean? And that's what always intimidated me when I got started on this. And as it turns out, most of the time we know what we're looking for, and there's tools to help us, and of course, lots of online forums and publications. But built into the software is a little reference library. Now, this is an A-star. This is Vega from my first night out. I'm going to open that reference library and say to it, oh, I wanted to show you something pretty first. We can do this color fill, which, again, really attracts attention at a star party. But here, I'm going to just click on hydrogen bomber. And now we can see where the hydrogen lines are. This overlay predicts where they should be, and our red data has absorption features. Dips, not all that close. Sometimes, I shouldn't point that out, but I will in a moment again. These dips are aligned more or less. Now, what really bothers me as a software guy, because I wrote the software. In fact, here's the story. Again, I went outside the windows right here in 2009. Let's see if I can get my screen or my camera to focus on me again. Sometimes it gets confused. You can't see me that well anyway, so it probably doesn't matter. But I went outside. I wanted to capture some spectra, and we'll let it be blurry for a while. And I came in at midnight with my C8 and a Logitech webcam duct taped to my telescope. And the next morning, I tried some of the shareware that was out there, some of the freeware, and it kept crashing. And then to add injury to insult, the crashes were in French, the messages instead of English. And I did something that at the moment I wasn't proud of. I just gave up. I went upstairs to my wife. I said, I'm not having fun. This is supposed to be a hobby. And what also is bugging me is my camera, I guess it's the vanity in me, isn't focusing on me. So what did I do? I took the grading and I threw it in a drawer and I gave up. I figured this isn't for me. But it kept bugging me. So about 2 weeks later, while I was making lunch one day in our kitchen, I thought, I'll just write the software. I've been writing the software for 40 or 50 years. How long can it take? So at Saturday, on a day off, typical weekend, I wrote the software. Next day it was done. And now, I guess about 20,000 hours of programming later, it's almost done. My wife keeps saying, would you finish the software so we could have dinner together? It's not quite that bad. But it's a lot of work. I didn't plan to turn it into a product. But what I want to show you as the software developer is this difference between our raw data and where we predict it isn't that great. This is in 4082, and we were predicting it at 4101. So it's what? It's 19 angstroms on this axis, different over more than 4,000.
So it's a 1 or 2% error, but that looks like a huge chasm to me when I look at that. And I'm again, there's other reasons that things get a lot better over time when we start. This is my first spectrum. Last thing I want to show you, just because it's pretty, this is actually a video. So what I'm going to do is play back the video. I recorded it at 2 frames a second. I want you to watch what happens. I'm going to zoom in on the star first of all. See how the star is changing from frame to frame? Some of you may know that's because, the atmosphere has heat currents in it, like, the hood of a car when it's heated up and you see the light behind it, the house behind it flickering, or the view over a campfire on the beach. You get that wavering. The stars do the same thing. Now, that's what's happening with the star. It's called seeing if you're not familiar with it. And so this is changing too. But for those of you who do outreach, if you're active astronomers, if you set this up at a star party, you will have a lot of interest. And that's because it's colorful and people are interested in seeing something as a group rather than through an eyepiece barely. And it will give you an opportunity to talk about things about which you know a little, much like I am today. All right, so that's the only demo I wanted to do. And it was longer than I had anticipated. So we're back to screen sharing. And again, there's a typical star party where you can do this kind of thing. This is in Marseille. And you wouldn't want to do this at a dark site because that's a pretty bright screen. But yeah, of course, you could also just do it on your laptop screen. Okay, let's race through some examples. I want to make sure that we leave some time for questions if there are any. And I know you probably have stuff out the doors there outside this dark room that you'd like to look at after my talk. So without defining much about these objects, I wanted to show you here's what's called the Ring Nebula. And you can see there that there really are just 2 images of it. This is a broad object, so it's one of the few that we can actually observe with an inexpensive device like this. If you want to observe, broad objects like galaxies and nebulas, like M42, then you need to put your money where your mouth is. We don't sell these, and they're hard to use because now you got to keep the star on a 10-micron slit. So you've got tracking and guiding, all sorts of stuff. But when you do that, then you can image really large nebula, like the Orion Nebula. And you can see really small, very tight lines. We won't get into much detail, but everything I'm going to show you this afternoon are things that you could be doing inside of a week. Really, literally the first night, people often get the kinds of spectra that I've been showing you. I'll tell you when I'm showing you examples that didn't use this, and that was the first of very few. Here's Uranus. We're seeing the methane absorption bands here. This is pretty exciting because and look, it was done with a video camera and a 4.5-inch telescope. You can see at the bottom of the screen there. Because once you can see methane, you're talking about the atmosphere of a planet, and that leads you to being able to discuss all sorts of things, exoplanets, ET, how are we going to discover life? And I wanted to mention something else, and that is, a lot of us do like to reach out and give back to our communities, and the association there that you're at is a great example of it. Astronomy isn't a very popular subject in our schools because they have so much else to teach. But you know what is? Chemistry. You can go to a chemistry teacher, especially if you had one of these gas tubes, and you can do a demonstration that ties the chemistry that they're capturing in classroom to astronomy. And that can really catalyze a big turnout at a star party, and it can be a very rewarding project for you to do. So here's 9 quick reasons why you might want to do this. I don't know, those of you who've captured images before may remember that first lunar image. Mine was blurry like many people's, unfocused, overexposed, but to me it was the most beautiful image I'd ever seen. Thrilling. I was showing it to my wife and my coworkers and my friends, and they're going, okay, yeah. But that thrill is something which you get again when you start doing this kind of thing. And you also get to learn science inexpensively. And let's see, oh yeah, this is really important. All of the people who use my tools tell me this. And that is when it's your data, all of a sudden it becomes more interesting to read about. It's not just a dry Wikipedia entry. It's like, oh, I just captured that data. as I mentioned, you don't need dark skies or a Ph.D., and you don't need to have lots of time. You know, I love those gorgeous images. When I give these talks in person, like at NEAF, which is a nearby conference to you, I often at this point will ask somebody in the audience to pull out some astronomy magazine, turn to the back, the showcase section, and point out just some beautiful, gorgeous visual images of some galaxies. And then I have them read the fine print. And it's like literally it's 25 hours of imaging time over, several months, and mountaintop and huge telescope and 20 years of imaging experience. I don't have any of that. And the cool thing is I don't need it to do this stuff, and neither do you. I'm glad those people do that, because I need to cover my rear end by saying this, and it's true. I'm glad they do it. I don't mean to discount imagers, because the images they produce really capture our imagination, which is what this is all about in the end run. I think in the end, it's getting a sense for us living in this enormous universe. The passage of time is enormous, and somehow it makes us feel small. Also diminishes our troubles in the big picture, but it also somehow makes us feel big. And I think those are deep human experiences that we seek. And there's lots of ways to get them. The more the merrier, I say, whether it's loving your grandchild, being a silly 2-year-old, or looking at a rose, or solving a math problem, or looking into your spouse's eyes, whatever it is. Astronomy, I think, for everybody who does it the way we do, captures that, standing under that cathedral of stars at midnight with people who share the same image, the same vision. So this is easy to do, and you can do public outreach. Okay, that was a lot more philosophical talk than I normally do. Let's keep moving. In 1881, Henry Draper captured the spectrum of a comet. If Hank can do it, so can we. There's a comet in the left-hand corner, and there you can see it's in the image, this little string of gems plotted out on our software here. Again, without getting into a lot of the details, that's called the Swan bands. And this was captured by Vikrant Agnihotri, who lives in Rajasthan in India, using a tiny refractor and a DSLR. So here's another comet, just to show you these things are possible. Generally, comets are too broad to get interesting spectra, but a compact comet works fine. Now, this next one is really sort of fun, really quickly here. This guy took a video camera, put a star analyzer on the nose piece, and then bracketed it inside a C-clamp onto his tracking mount. Now, if it was me, I would have tightened that C-clamp down too much and collapsed and destroyed the camera. That's why I like software. There's always a Control-Z. In fact, sometimes I wish in life we had an edit undo option. Wouldn't that be great? If you could say, hey, let me just rewind the tape 90 seconds or 10 years. So, but down here, you can see the spectrum he captured. That's like a half-second image. And the comet is moving in that direction. And this thing here is the comet. And then the comet's spectrum is here, and that bright spot is it brightened for a moment. And over here is some of the minerals that Robin Leadbeater identified. It's pretty esoteric, but sort of fun kind of aspect. If spectroscopy is a niche, this is a niche in a niche. I'm not going to get into solar spectra. We've had a lot of that over the last several years, but I do want to remind you what Doppler shift is. Really briefly, let me check the time. Really briefly, Doppler shift is, for those of you who can't quite recall, the pitch change that sounds make, for example, when they're coming towards you and away. When you're standing on the side of the turnpike with a flat tire and some person comes through, I was going to call them something else, with their horn on the whole time, what's it sound like? Right? Higher coming towards you, lower going away. That's Doppler shift, and it happens to light too. So if we were expecting to see a spectrum with this triplet here, love that word triplet, self-defining and not often used, is it? Except in progeny. If we didn't find it there in our data, we saw it there, we'd know the object was moving away from us, like that car horn, moving away. And the same thing if it was shifted the other direction. Let's look at a really cool example. Okay, a little background here. This will be the shortest description of what a supernova is. It's the end of a life cycle of a star. Some stars run out of fuel. blow up, collapse on themselves, blow up. This particular type of supernova, 1A, is two stars orbiting one another. One's big. Some of its gas gets gravitationally sucked onto the smaller one and it blows up. And when they blow up, they are brighter than all the stars in their galaxy, the billions of stars, for a short period of time, hours, days, weeks. So here's what one looks like in an animation. This is just somebody's image of it. It's somewhat accurate. You can see that shell expanding as that gas that got dribbled onto the star, more sucked onto the star, explodes. And here's a supernova shell, like we just saw. This is a real one that they've captured with telescopes. It happened hundreds and hundreds of years ago. The light's just reaching us now, so we're looking into the past. This is what it looked like hundreds of years ago. It's a time machine. So, and here is the spectrum captured by David Strange with a 9-inch telescope and 15 minutes worth of exposure time. See that little gap there? Well, if we graph it in my software, that little gap becomes very clear. Now, there's definitely not going to be a question on the quiz about this next slide. You don't have to memorize this or take notes on it. But as I mentioned, there's lots of different stars, the ways that stars die. These are called 1A when the gas dumps on them. And these 1A stars have a deep dip around 6,000. They called here silicon. So this is the fingerprint of a collapsing supernova. These other supernovae don't have a deep dip there, do they? This one's a little offset. This doesn't. So if we see this dip, that means we're looking at a supernova type 1A. So let's do some really cool science with a single addition and a single abstraction, yes, subtraction and division. And I got to keep moving here quickly, so we're going to move this fast. How fast is that shell expanding around the supernova that went off hundreds of years ago and is just an unimaginable distance from us? Well, the first thing we do is we look at, well, where is that dip in our data? And it's at about 6150 angstroms. So let's write that down. Now let's look up in a book where this ionized silicon, which again, we don't have to understand it, we just are told that's what supernovae have dips in. At rest in the lab, if Bunsen had burnt some beach sand, he would have seen the same dip at a different wavelength because this is stationary, whereas this one's coming towards us. Now, look, I don't remember any of this stuff that I remember maybe seeing in high school. Here's the Doppler shift formula. One division, one multiplication, and one subtraction. And we get the speed of the shell of that supernova coming towards you. Now, again, if you've never encountered this before, forget everything I just said, except for the fact that somehow we used the color of this object to tell how fast it was coming towards us, much like that person coming past you on the highway when you're stopped changing a flat tire and honks their horn. In the same way their horn goes, ear, and if they were going by much, much faster, it would be, we can determine the speed that things are going towards or away from us by the pitch change. That's what we just did. In this case, the color change. Now, this guy,
Hey, Tom,
yes.
so that would be a great feature in the software for you to calculate that.
Yes.
That to the
That's a
user.
good, wait, let me write that down. I've heard it before, but these kinds of things slip my mind.
There you
So
go.
supernova RV is sufficient. Okay, thanks. So Adam Rees, most of what we've been talking about is stuff that's been done 150 years ago, but not this, not Adam. He won the Nobel Prize. Should I call him Dr. Rees? Probably. He won the Nobel Prize for work that he and his team did in the late 20th century. Seems like ages ago. And he's the one, his team discovered that the cosmological expansion seemed, God, that fuzzy image of me bothers me, seems to be accelerating. So I'm going to turn my camera off and on. That usually fixes it. There we go. So the expansion of the universe seems to be accelerating, although there's some question about that now. And he won the Nobel Prize for it. And guess what type of star he used? He used a type 1a supernova. So now, with your $300 piece of equipment, right, $200 software and a little grading, now you're able to use some of the same measurements that a Nobel Prize winner won. Now, there's a considerable distance between what we can do and what these people do with their equipment and their knowledge. But we're sort of climbing on the shoulders of giants, right? We're getting closer to the present. So he actually commented on some of my work. I probably won't have time to discuss it today, but what about the spectrum of a black hole? Well, a black hole, of course, is black. There you can see it in the center, but the gases that are spiraling in the accretion disk, they're visible and they're hot and they are glowing. So let's look at one. Now, all of you, again, I'm joking here, know our familiar 3C273 in this field of view, right? Just jumps right out at you. David Hayworth in Portland, Oregon, down the road from us here. I'm in Seattle. He observed it at its spectrum. Notice the two little dots on those right arrows. Let's blow it up. There's those two little dots. When you plot it, you see this curve. And so what this guy, Martin Schmidt, did, he was 25 years old, plus or minus a few years. I can't recall. He looked at this and he went, oh, what is this? So he did what every scientist does and what you'll be able to do. He compared an unknown to a known. And what known did he use? Well, I meant to point this out on my software. He used that overlay, those hydrogen bomber lines. This is the bomber series where hydrogen emits light. And when he compared the known here to the unknown, he didn't see anything lining up, right? It's like, well, maybe there's some matches, but nothing significant. So he concluded, well, I guess whatever we're seeing, this doesn't have hydrogen on it. But he was wrong, and he figured it out. Those were hydrogen emission lines, right? Bright spots that were happening because of huge redshift, because of how far away this object was. The Doppler shift, they don't call it that, as our Nobel Prize winner in the previous slide corrected me. They don't call it Doppler shift. Why? Get this. Nothing's moving. What? Cars move and give us Doppler shift, right? Trains go through stations, right? Why? This is changing from the distance increasing. Why don't we call it movement? Doppler shift. Because, as Dr. Rees said to me through an email, nothing's moving. I mean, really, that's sort of fun to think about. It's getting a further away from us. It's getting a further distance from us, but it's not moving. It doesn't have any velocity. The space is dilating, expanding. Now, I don't know exactly how to think about that, but it's fun that by doing these kinds of projects, you can begin to touch this kind of data. And our data is pretty accurate. So I wanted to just marvel for another moment that this light that is 2 billion light years distant still has information that we can capture with our amateur telescopes and understand something about this object. 2 billion years, this light doesn't seem to age. And maybe it doesn't when you talk relativity. But humans, unfortunately, do age. And this is Martin Schmidt a few years ago. Friends have accused me, rightly so, of throwing him under the bus. Listen, he's got a full head of hair. It's okay. I'm a little envious of the guy. He's since passed away, but a great guy. And if nothing else from this talk, and I hope there are other things, if you're interested, go to our site and send me a contact form. I won't hit you with spam. And I'll send you a link to a written transcript of the interview of how he discovered this. And it's fascinating. He's sharing his personal experience, how he made that original mistake and then corrected it. How when he went home, he said to his wife, something terrible happened today. And she said, what? And he said, I made a big discovery. She said, how is that terrible? And he said, I'm not going to get any peace and quiet because I'm going to have news reporters and all sorts of people. He was there in New Jersey, by the way, at Princeton.
I'm going to have, I want to just do my science. Again, if his last name happened to be a Kardashian, he would have been seeking that fame for nothing. In his case, the fame meant nothing to him. So anyway, fun little story, but you can contact me and I will send you that transcript. Honestly, nobody ever has, and I've given this talk hundreds of times. I challenge you, not because I really care, except I want the pleasure of sharing something with you that will really blow your socks off. It's not science, it's this experience as a scientist. This is an example of the kinds of projects you can do. Whether you go into chemistry classes, if you do, you can cherry pick the bright students. They'll come to you, they'll self-select, and then you can capture data. And this, look, it looks like there's some fancy formulas in there, but there's nothing here that you can't do with a little tiny calculator. I'm going to show you one other example of this email here. You can all read that, of course, right? Well, there it is. We don't have time to read everything. Nicole reached out to me last fall and said, you know, I don't really have this kind of money. Could I do something for $5? I really want to do spectroscopy. It's like, that's waving red meat in front of what do you do, a dog or a lion or something? So I tried to find a professor in her town and almost did, but she was retired. And I finally reached out to the Astronomy Club. And I was fortunate that their president was an active imager and interested in helping. We gave her and him the software. We lent them a star analyzer that had been donated, the funds for which had been donated by an astronomer in Switzerland for whom we'd done this with one of his students. And then they went out. I tutored her a lot online. They went out and captured spectra. And she won her school, her region, and her state science fair. And then by winning, I mean she came in first place. And here's her poster. You could coach students doing this, and it would change their lives, and I dare say it would change yours too. Don't believe me? Call my bluff. Try it. Want more information about it? Let me know. Our software also works, as you can see here on the left, with gas tubes like the one I showed you. And we have this little gas tube, little tripod-mounted spectrometer that you can take into chemistry classes. We have several thousand schools running that little tripod spectrometer in chemistry, astronomy, and physics classes, and all of the Ivy League schools. And you could too. So I'm not going to get further into this. I'd love to have time to. We don't. Two more quick examples, really quick. We've been looking at things as big as that, which are about 50 microns or angstroms across. If you want to zoom in on that, first of all, you don't shut down your Zoom talk, your PowerPoint show, but what you do is you use one of those expensive slit spectrometers, and now you can see the difference in color in this feature, which is that, between the moon, which isn't moving towards or away from us, and a star. Final example tonight, and that is a spinning star, very fast spinning. This edge is coming towards you. This edge is moving away from you, very fast spinning. So you get that Doppler shift again. So some of the light is blue shifted when the edge is coming towards you, and some is red shifted. So instead of seeing a deep, sharp dip like this, you see this broad dip. The colors are spread out. This requires a slit, one of those expensive, hard to use slit spectrometers, but it's pretty cool. It's just an example of the kind of science we do. Okay, just a race across the finish line here. How do you get started? You get our grading. Number one, you get some camera, almost any camera, color, mono, AVI, whatever. You get software. This is my software, RSpec. This is that freeware I mentioned. I know these people. They are enormously big people in what they've contributed to the hobby, and as well as the science. And they've improved their software a lot over the last 15 years. Good people. And maybe you need a thread adapter to have that spacing be about right. I help people do that. Worried about how to understand this stuff? These are all Patrick Moore books, or at least the top row is. And those are, you may recall, thin paperbacks aimed at us. They're all on my site. Our forum exists. The AAVSO has a database you can contribute now, Spectra to, and the software is free for 30 days. About 5 years ago, I gave a talk to about 100 AAVSO members at a conference that they had. And it wasn't only a talk, it was a workshop. and we walked through how to do what I'm showing you here. And we recorded it, and the sample data are both available on my site. So tonight or tomorrow, Sunday morning after your cup of coffee, you could sit down, download that software, preferably with 2 monitors, watch the YouTube on one, run my software, the sample data on the other. Whether you ever do this with a telescope, you would have your eyes opened in a great way to what this is all about. There are opportunities to contribute to professional pro-am projects. There aren't as many as we'd like. Most of the names in the author block of this, and the second section are amateur astronomers. So there's our map, and I've just been dragging you by the nose all over the map. And my goal was that you come away with at least an appreciation for how this is done, and that maybe you could do it, and that you have a added admiration for what, if I was a poet, I'd be able to describe better. But the enormous achievements of humanity in understanding the world around us. I want to thank you all. And if there's questions until Jimmy tears me off the stage, I'm here to answer them. You can see the URL there and my email address. If I hear from you, I'd be really happy. If not, I hope you enjoyed, and I hope going forward that whatever you do in astronomy is something that is rewarding for you. Thank you all.
Tom, thank you for a great talk. Round of applause for that.
Great. I stopped screen sharing.
Let me turn the camera on. Is somebody in the back can turn the lights on? NJAA. Thank you. Here we got some questions here.
Oh, there's the audience. Great.
Get this in focus when we get some light. Right?
Hey, that guy who was sitting front and center took off. I hope
Yeah.
that I hope.
Wow.
There he is. Maybe he came back in the door. Regardless, I'm glad some of you stuck it out with me. If you've got questions.
Let me try this.
Oh, there. Yeah.
Better?
Nah, try turning the camera off and on. Sometimes that works from Zoom.
Interesting. One more time.
Nope. Actually,
Wow.
I just turned it on a moment ago,
All
so
right.
that wouldn't have been a solution. All right, that's okay. I can see well enough. If I take
We'll
my
just go
glasses
to
off,
blur.
maybe it'll get unblurry.
Are there
What's
any-
up? Any questions from the group there?
Gotta be questions. Some questions. Yes.
Are there any specific citizen science type projects? So I do astrophotography, and I was always interested in trying to do exoplanet transit research from my backyard, which is kind of ambitious. But
Yeah.
I'm wondering if there's anything like that.
There are for exoplanet transits. I don't know if you're familiar with the fact that there are organizations available that will help you predict when they're going to be, and when you capture that data, you can submit it, and that helps them polish their data. It is doable. It's not something that I'm familiar with. It's fairly exacting work. You may have heard my hesitancy and the sort of equivocating when I mentioned pro-am collaboration, because these days, especially with the airborne and spaceborne platforms, it gets harder for us to make meaningful contributions. But what we have that the professionals don't is time. We can be observing things that they just can't get access to on their telescopes and on mountaintops or on satellites, because the time is so precious. So there are pro-am collaborations. AAVSO does have a database to which you can contribute spectroscopic data, and we're hoping for more and more. In fact, I've been working with the AAVSO continuously, but more actively over the last 6 months. And they've just published a spectroscopic atlas. So there are opportunities, but I don't want to oversell them either. I know all of us want to make those kinds of contributions. And like I said, it's fewer and far between that we can do it, but it's still possible. It's a good question, and I'm glad you voiced it, because all of us feel the way you do, I think. Other questions or follow up on that if you have one.
No, that's great. Thank you.
Sure.
Somebody else has got to have a question. That means I have to throw in a couple. So Tom, with the gratings, looking at, is there an optimal focal length? Is there an optimal focal length for the 100 and the 200? My basis for that is it better to have a longer focal length and stretch out the light across the pixels for analysis?
Good. That's a good question. Without getting into too many of the details, we do have a page on our site called the calculator where you plug in your camera's, specs, how big the pixels are and what your telescope focal length is. And it tells you which of the two gratings that we have that are best for you. So you don't want too fast. Again, technically, oh, now it's focused. So you don't, I don't, this is not a good joke, but I can see that there's like some people still, have sand in their eyes from the sleeping they were doing during my presentation. And that's my shortcoming, not yours. You don't want too fast a telescope. Anything faster than F4 is too fast, and F10 is generally too slow because things are too spread out. But even an F10 SCT C8 works sometimes with a focal reducer. So I'm always happy to coach people on that because it is a little bit of a speed bump going forward to get started. Is like, well, how do I mount this? Is my telescope and camera going to work with this? And are my telescope and camera going to work with this? It's pretty easy. Just if you send me your equipment specs, we can do an email or two and I clear it up.
Okay.
It's not like building a telescope or building a camera where you have to, as I mentioned earlier, use a micrometer and all this fancy tools to measure things and get it just right, just approximate in the range. I'm pretty casual, and my reputation amongst people who are less casual isn't great, I have to confess. And that's because, oh wait, there's that fellow over on the right with the glasses is just nodding his head. Yes, I'm embarrassed now. Yeah, you. Anyway, my goal is not to turn you into a scientist. And I think a lot of higher end people in every field tend to lose sight of the fact that we all don't want to become those professionals taking things out to 5 digits. My goal is to get people involved, get their feet wet, have some fun, learn some things. I think there's a much larger group of people who want to do that, and there's more of a impact that we can have by spreading that kind of experience than just training the handful of people who are going to go on to get their PhDs. So, anyway, other questions anybody have? Jimmy, you want to feed me one more, or we're sort of out of time? That's fine.
Just the last one, future operating systems that the software may be operating on.
Well, it's Win 10, Win 11. We have a version on Mac OS, but it's just for classrooms. Sometimes people run it under Wine, under crossover on Macs, but mostly it's a Windows 10 app. Yeah. It's not like for some of you who seen or perhaps even seen discussions. There's software out there where you end up. I've been at conferences where I've seen this go on. I set up a table. I'm expecting to talk to a lot of people, which I love to do, and people are going for 3-4 hours a day for 3 days in a row. And I go, what's going on here? It's like, oh well, they're taking the workshop on how to use brand X software. It's not spectroscopy; it's imaging. Some of you know what I'm talking about, but. Yeah. The powerful software does require oftentimes a lot of training. Mine is not that. It comes with several dozen 3-minute videos that walk you through, like I'm sitting with you, how to use the software. I'm retired from my real job. This is fun. There's nothing I enjoy more than showing people how to succeed with software and seeing their first images. So one of my goals, which I try and accomplish in these talks, is to remove the intimidation factor, because we're all intimidated, and all of us, and there's no reason for that. And I'll help you get past, I used the word speed bumps earlier. Just my final comment here in this talk is in England, because we have users all over the world. In fact, I'm coaching a 8th grader in New Delhi right now. And she's going to workshops that we put together. And I mean, she's scary smart. And scary because she's going to make me look bad. That's, again, the insecurities that we all have. But now that I've distracted myself and can't remember, I know, speed bump. In England, that's the international connection, they don't call them speed bumps. They call them sleeping policemen. That's a funny term. Maybe in this day and age, it's not a good term to be laughing about, but all the same, I love those kinds of language differences that cultures have. Anyway, everybody, thanks for coming
All
out
right,
this
thank you,
afternoon.
Tom. Thank
You're
you very
welcome.
much. I appreciate it.
Great. Have a great afternoon, and congratulations. Thanks for the applause, all of you. Good evening. Afternoon.
All right.
Bye.
All right, thank you, Tom.
Sure.
Be well, stay safe.
You too. Thanks.